Allow me to introduce to this man here, Telmo Fernandez Castro, a dear friend of mine that is the director of the planetary in Madrid, an astrophysicist that is doing a great job in communicating the latest news about the universe to humanity. This is a translation from one of his lectures, which happened during COVID. So this is part of a program that was planning to bring the universe to the house during lockdown, to the houses of millions of families. This video had already more than 1.5 million views in YouTube. So I thought it was a treasure that should be shared in English with some bigger audience. And I asked Telmo if I could record over his voice in English, or if that would bring an issue with copyright. And his answer was, everything belongs to everyone. So with that generosity, I am going to share this wonderful lecture, wonderful talk about a curious history of the universe by Telmo Fernandez Castro. And there we go. So he is introducing the program. He's saying that this is the first video, a general video, just to bring the passions that astrophysicists have with everyone that is willing to learn, right? So he starts the lesson from the Earth, of course. We start from home. This is our Earth, a planet that will zoom out just to see our place in the universe, to understand our size and position in the universe. We will travel from our home, from the Earth, to the edge of the universe. The Earth is just another planet in the solar system. It's a planet that is orbiting around the sun. So we call a solar system a planetary system. It is a system that is made of 8 planets orbiting. They all were formed from a grand cloud of gas, a gas cloud that conserved all this rotational inertia, the momentum that gave birth to the sun and to the planets in the same direction of rotation. There are also satellites around the planets. There are asteroids in the solar system. There are comets in the solar system. And here is where we live. This is our home, a home that right now is suffering, unfortunately suffering hard times due to the virus. Such a huge universe and such a tiny virus. So this is our Earth, part of the planetary system. Everything is orbiting the sun. The sun is our closest star. All this evolved around 4,600 million years ago. And with time, these planets that evolved from the same cloud have a different dynamics and belong to a bigger stellar system. This solar system, this volume that is including the sun and the planets, is part of a galaxy. We call our galaxy the Milky Way. So there we can see in the image the sun, a tiny spot of light in the galaxy, and the solar system is part of this galaxy. It orbits in space with the galaxy. The galaxy has approximately from 200 to 400 million stars, and the sun is just one of them. So when we look at the sky at night, any night, if we are able to escape from the light pollution of the city, we can see some thousands of stars. And all the stars that we see, all of these stars that we see at night, they belong to the galaxy, to the Milky Way. That is what we call our galaxy. Like I said, it contains around 200 to 400 million stars. But that is not the only galaxy in the universe. We live in a universe where there are many, many, many more galaxies, up to 100 million galaxies in one cluster, just in one cluster of galaxies. And all these clusters make also millions in the universe. Everything that we learned, that we know now, is quite recent, because we have the instruments to look further in space-time now. Instruments that are not just installed on Earth, but also orbiting the Earth. Telescopes, radio telescopes that are orbiting the Earth. These instruments allow us to travel to the moon, for example. The moon is our natural satellite. We've been able to walk on the moon, send human beings to the moon. We've been capable of reaching the moon on that natural satellite. But that is because it's very close to us, only 400,000 kilometers. It's very close to us. That's why it was possible for human beings to travel there, right? But beyond the moon, we have not reached with human bodies, but we send spaceships. These spaceships are able to travel at high speeds and reach the orbits of these planets within our solar system. So we've been able to visit the atmospheres of some of these planets, even deposit some machines, some rovers, like in Mars recently. And in some cases, and like in Mars, I said, or Venus. Venus is a planet that has an atmosphere that is very aggressive, very acidic. So it's corrosive. So we even sent spaceships to that atmosphere before they disintegrate by the action of these corrosive atmospheres. Also, we've been able to send spaceships to Saturn, like Titan. We send a Huygens spaceship to the surface of one of the moons of Jupiter. So we are able to study these satellites to see how similar they could be to our Earth, or at least to our Earth some time ago. The problem with the astronomy is that we are unable to send spaceships beyond the solar system, not even with spaceships. The distances are so far. We've been creative. We've sent spaceships as passengers of a comet, like the Rosetta spaceship. Philae was deposited in the surface of the comet, and the comet takes this around the solar system in very, very big orbits. So this gave us a lot of important information about the origins of the solar system. But if we want to really know more about the universe, we only have the option of seeing from satellites that are orbiting the Earth, or even from the Earth itself with radio telescopes. So this is how we understand the language of the stars. This is how we decode the language coming from the stars, the language that comes from the galaxies in the form of light. So these instruments are capable of giving us information about the probable origin of the universe, information about the background microwave radiation, which is what remains from that Big Bang, from that initial explosion that gave birth to this universe. Or even information about black holes that hide mysteries totally unknown to us. We don't know what happens inside these black holes. So the space agencies like NASA, the European Space Agency, are able to explore beyond the solar system. Here in Madrid, we receive a lot of that information. We receive the information from those distant spaceships that we can analyze in Spain in order to understand the nature, the real nature of the universe, and explore the mysteries, the meaning for our existence here on Earth. Are we a planet that is inhabited in a desert universe? Is there life beyond Earth? All these questions could find an answer eventually. One of the strongest evidence that has been discovered at the beginning of the century is the fact that the universe is expanding. Big objects like galaxies that are observed in the universe have been observed to be extending the distance between them. This is one of the strongest evidence for the Big Bang theory. The fact that the universe is currently expanding its space in between the galaxies is actually expanding. It's not that the galaxies are traveling far away in space, it is space itself. And this is what we can see by the red shift of the light that reaches us from the galaxies that are far away. The red shift means that the galaxies are moving away from us. Not just from us, but all galaxies are moving away from each other. This is, for example, a good way of observing this model. It's not that the galaxies are traveling far away in space. It is space in between galaxies that is expanding. It is as if a chewing gum is stretching, and we plot dots on that chewing gum to represent the galaxies, or in a balloon that is inflating, we draw dots. And the dots, as the balloon expands, will spread away from each other. This is exactly what the evidence is showing us. So when we look at the space in further away in time, the space-time web, or the space-time, is stretching. The tissue of the space-time itself is stretching. This is important to understand. It's not that objects are traveling away from each other. It's because the fabric of space-time itself is expanding. This is giving us an incredible advantage, because it means that we can understand the history of the universe by looking further away in space. That means further away in space is further away in time. So we are able to know about the past of the universe by looking back in space. To be honest, there is no image of the present state of the universe, Because when we look into space, we only see past. Like, for example, the closest star to the Earth is 4 light years away. So the light reaching us from that star has left the star 4 years ago. And when we look deeper into space, we're looking at light that traveled million years. So this is not a picture of the present moment of the universe when you look at the universe, right? And this is the law. This image that we see here is a law that gives a mathematical equation to this expansion. This law was discovered by Edwin Hubble based on a model described by Georges Lemaitre. Georges Lemaitre was a priest from the Vatican, a mathematician, priest. He was from Belgium. And both of them, based on empirical evidence from the redshift of the galaxies, reached to the conclusion that the further away the galaxies are, the faster they move away from each other. And that constant of proportionality between the speed and the distance is what we call the Hubble constant or the Hubble parameter. It is the gradient of that line, represented by the letter H0 there. So if the universe emerged from a Big Bang in all directions, there should be a remaining, like a fossil residue of that explosion. There should be evidence of that Big Bang further away in space. So this was evidence that we've wanted to find during many years. And according to the mathematical models, it should have been a radiation emitted around 380,000 years after the Big Bang, because it was only then that the atoms or that the universe was transparent to radiation. It was possible after 380,000 years for light to be able to travel outwards in all directions, and that radiation should have cooled down over time. But this radiation was very hard to find. Finally, in 1965, Penzias and Wilson, in an experimental coincidence, they were not looking for it, they were investigating radio communications with microwaves. These were working for the Bell Company. They discovered that in every direction there was some kind of noise, like a background noise that was altering the appreciation that they wanted to find. They were not sure what they were discovering. They were thinking that probably that had something to do with poo from birds or some kind of pollution in the antenna. But that discovery, in fact, was the discovery that matched the theory. It was the beginning of understanding the Big Bang theory in depth. This is probably one of the most important cosmological discoveries because it confirms the Big Bang theory. At least in this universe that we are observing now, this could be the early stage of this universe, which we don't know if it's the only possible universe. So we're looking at 380,000 years after the Big Bang, a picture of the universe. From that Big Bang, at least, we have seen this background radiation. And then this background radiation was observed every time with more and more resolution, more and more precision in the observation. In 1992, the COPE satellite with a 7 degrees of resolution, angle of resolution, gave us that image. So now it was not so uniform. We see some shadows there, right? In 2003, the WMAP satellite with a bigger resolution gave us even more detailed images, and the recent images from the Planck satellite with a very, very high resolution camera gave us very high precision. And that is the evidence that the background radiation is not totally uniform. And this is the latest picture of the first moments of the universe. So this is the Planck scanning the sky, scanning the background of the universe, and looking only at microwave radiation, because this is what was expected to find. This radiation was expected to be so far away in space-time that we could observe it only as microwaves. And the map of this radiation is this picture that we record there. Every color is just giving us different zones where there are some asymmetries, some anisotropies in the universe. Those tiny differences represents differences in temperature. Those are the seeds for the galaxies. Because of these asymmetries, we can now understand the structure of the universe in terms of galaxies and other matter that we will explore later on. We will look at the chemical composition of the universe later on in this lesson. So this is the image, the most modern image of the most ancient time of the universe. This radiation, like I said before, was emitted only 380,000 years after the Big Bang. Today we believe that the age of the universe in which we live is around 13,800 million years. 13,800 million years old, from the Big Bang till today. So there is no way of observing any radiation before the first 380,000 years. That light that came out of the universe started to cool down and is now in the region of the microwaves. And what is very interesting and very important to outline here is that it doesn't matter in what direction we observe. In any direction, we are surrounded by this omnipresent radiation in every direction. So when we observe with a television, with an analog TV, that noise, that background noise, or part of that background noise, is that background radiation, microwave radiation. And that is the result, like I said, of the birth of the universe from the Big Bang. One of the important consequences of understanding this radiation is that we can understand the geometry of the universe. How light travels through the universe and the possible fates or destinies of the universe. Will the universe continue to expand? Will the universe start compressing into a big crunch? Or will the universe continue to be eternally flat? This is the importance, or one of the importance, of this background radiation. We can predict a mathematical model. According to the values that we are now understanding, the geometry of the universe is plane, like we see here in this image. That means that the universe is expanding progressively, but the data is still very preliminary. We are only beginning to understand the universe. We have only explored it for the last few decades. So we are only in the beginnings of the understanding of this evidence. What is interesting again is that the background radiation determines the geometry of the universe. And again, it seems as if the universe is flat. So at a big scale, the universe is Euclidean. Geometry is plane. Light travels more or less in a straight line, generally. Only in areas when there is a high concentration of matter, where light is affected by that gravitational field. Another important aspect that validates the Big Bang model is the chemical composition of the universe. The observed composition chemical of the universe is in agreement with the Big Bang model. When we look at the matter of the universe, when we observe what the galaxies are made up of, what the stars are made up of, and even what us and the Earth is made up of, we see that most of the matter in the universe needs to be formed in the first instance after the Big Bang. And according to this model, 75% should be hydrogen. 75% of the material content of the universe should be hydrogen. 25% should be helium. And then there is a very tiny fraction of light elements from the periodic table. Very tiny fraction, but most of the universe should be composed of hydrogen and helium. The rest of the chemical energies, the rest of the chemical elements, the rest of the atoms did evolve not in the Big Bang, but inside stars because of the nuclear reactions inside the stars, because of the high gravitational fields in the stars. So these are cyclic phenomena that are formed from stellar clusters, from clouds, and depending on the size, the amount of matter, the evolution of the stars is different. So they can generate different elements, different stars, different types of stars. Massive stars evolve fast and create great explosions, supernova explosions. And in those supernova explosions, some elements that are heavy are created, and they evolve to black holes or neutron stars. So in these supernova explosions, some of the heavier elements that are present in our bodies evolved. So not all of the chemical energy could be formed in any star. Very heavy elements can only be formed in supernova explosions. For example, in our sun is a third generation star. So it's quite a small star. In the origins, it had matter from these supernova explosions. But right now, the destiny of our star, the sun, is a red giant and a white dwarf. So we are in a standard model of the Big Bang now in science. We understand that everything evolved from a big explosion. It is not that the Big Bang happened in a point in space. This is all of space in one point. So this is the beginning of space and time. I understand that we are talking about things that are counterintuitive, but physics is counterintuitive. Modern physics is counterintuitive. So this model is very good to explain most of our questions. Now, the first question, is this model consistent with all the observations? Well, to be honest, already in the 1960s, some of these issues were questioned. The Big Bang theory was questioned. One of the questions was solved, finally solved. When we look at the cosmic microwave radiation, the standard model of the Big Bang does not explain important things like how can the background microwave radiation so far from being uniform, far from being isotropic by being uniform, how could there be such a distance between the microwave background radiation that there was no way of understanding how this could have been formed, because they were separated by a greater distance, as if the universe didn't have time to express this size, like two twin brothers being so far away in time that they could have never have met before. That was a contradiction, a paradox of this model. All this radiation that is around our system is so big that there is no time to understand that there has been such a rate of expansion for regions to be so far away in time that they could have never been together. So this was one of the paradoxes. There is not enough time in the history of the universe for these points to separate so much. But this was solved with a new theory, and we call this theory, this is called the problem of the horizon problem, the horizon problem. And to solve the horizon problem, the astronomers invented a model. You know, all models are in fact invented, and then we see if they work or they don't. So they invented this inflational model, the inflation. And this theory suggests that there must have been a very, very short period in time where the primitive universe experimented an enormously huge expansion. So the physical distances would have increased so fast during those initial inflation periods. So areas that were together initially suddenly became far away from each other. So there is no causal communication between them. So this is an illustration to understand what it means, right? As a sphere is inflated, it is curved, eventually it becomes undetectable. So the surface appears to be flat. If it is inflated by a factor of 27, right? So this needs to have happened so close to the Big Bang, like 0.35 zeros, then a 1 in seconds. 1 over 10 to the 35 seconds after the Big Bang, the universe should have expanded 10 to the 50 times its size. Unimaginable increase of size for an unimaginable fraction of time, right? Very difficult to understand. So the universe in 10 to the minus 32 seconds expanded to 10 to the 50 times its original size. But this theory gives a good framework to understand how we see the universe now from the Big Bang. What could be the origin of that inflation, quantum fluctuations in space? We need to understand space better to explain this. We need a theory for quantum gravity to explain this. But this is what we have seen, right? Something very interesting also to understand here is how big is the universe that we are able to observe. Before, I mentioned that when we look at the universe, we're looking at the past of the universe. We're looking at objects as they were sometimes 4 years ago if it's a close star, sometimes millions of years ago if it's a galaxy. And when we look at the background radiation, we're looking at the most distant images in space and time. But that doesn't mean that that is the actual boundary of the universe. That is a boundary to the observable universe. So for example, let's take an image of where we are in the universe. So we are in a galaxy. That's our galaxy in the center of, and from there we observe everywhere around. So we have other galaxies, other clusters of galaxies separated from us in space and in time. And we have a boundary there, which is the background radiation. There we are looking at emission of light or radiation that is far away in space and time. And that took some time to reach us. So if we want to calculate the radius of the universe that we can observe, that is called the observable universe, we have to take into consideration the amount of expansion that the universe had experienced during the time that light was traveling towards where we are now. And that gives us a size of 46,000 million light years. This is what we are able to observe. So that is what we call the observable universe. 46,000 millions light years. This is a picture of where that background radiation is after the expansion of the universe. But we have to consider that we are limited by the speed of light. The speed of light is not infinite. The speed of light is almost 300,000 kilometers per second. And there is nothing that has matter that could travel faster than light, right? Or anything, no radiation, nothing can travel faster than light. That is a postulate from relativity. But the problem is that we could center ourselves in another galaxy. So in that place, there would be another observable universe. Therefore, we can only be in different parts of the universe and see a bigger universe than what we see, right? In fact, there could be objects that are further away from what we can see. That is because the light has not had the time to reach us. So we have no idea. I think we'll never have an idea of the real dimensions or size of the universe. We are limited by this postulate, this principle stated by Einstein, that the speed of light is a universal constant, and that is the maximum limit at which energy travels in space. This is the only tool we have to understand the universe so far. Now, let's get things more complicated. Let's go into the next mystery.